Solve the examples in this chapter on your own and use the film to verify your results or in case you just don't know how to solve it. Okay, solution to A. We start with one knot, and when we go one step down, we have two knots. We go another step down, we have three knots, and so on. So when we have the depth 5, this means we have 6 leaves. B. Leaf number 2 means this leaf here. How many paths are there leading to leaf number 2? So for example, this is a path, or this is a path, here is a path, and so on. So how many possibilities are there? All paths leading to this leaf here consist of 3 steps to the left and 2 steps to the right. So we can describe them e.g. as left, left, right, or right, right, left, left. So this means by 2r and 3l. So this means we have all permutations of 2r and 5l, and we get hence 5 factorial, the total number of elements, divided by 3 factorial times 2 factorials, the repetitions. The alternative way to look at it is to say we have 5 steps in total and we want to choose the 3 steps where we want to go to the left. Which means that there are 5 choose 3 possibilities, which is the same like 5 choose 2, namely the 2 times we can choose where to go right, which is absolutely equivalent. And this leads now directly to the solution of C, where we assume that we have a tree of depth n, not only 5, and we want to know how many paths lead to the leaf number k. So this is leaf 0, leaf 1, 2, and let's say this is k. Well, obviously, to get to leaf k, we have to go k times to the right. If we go here, leaf k, so the 3, we have to go 3 times right. So of the n steps that I'm taking, I have to choose the k that I want to go to the right. And hence I get n choose k as the final result. Okay, let's get to example 2. We can look at that exactly the same way as example 1 as a binary tree. And when in the tree we go to the left, we get a white ball, and we go to the right, we get a black ball. And then we have exactly the equivalent task. We can look at the problem also directly. We're drawing 10 times the ball, and out of the 10 times we choose now the 3 times when we draw a black ball. So obviously we get 10 choose 3 possibilities. We can, for example, draw a black ball in the first, second, and third draw, or we can draw it in the first, third, and fifth draw, or in the 7th, 8th, and 10th draw, and so on. B is then just a generalization of this, which means we are drawing n times, and we want to look in how many ways can we draw k times the black ball, and we have to choose the k times out of these n drawings where we draw a black ball, which means we get just n choose k. Example 3, we're getting back to the opening example about sheepbirth. So here comes the solution. How many different tables are there with Julian participating? Well, this means there is Julian and 3 other persons. So we have to choose out of the 7 persons, 3 persons. So we get 7 choose 3. Well, per table, Julian can partner with each of the 3 other persons sitting at the table. So there are 3 constellations once the 4 people are known at the table. So now we have just to multiply the number of tables with the 3 constellations per table. And we get 7 choose 3 times 3, which equals 105. Here come the results, for example, for A. And now B. There are 10 places to choose from for the first person, 9 for the second one, and so on, and 5 for the last one. Or we can use then just the formula that we have for the variations for when we have 6 persons out of 10 and we want to select them, and the order matters. Well, in C, a little bit more complicated. Here comes the solution. There are 8 places for Alice to sit down, since on the left and on the right there has to be space for a friend. For the person on the left, there are 5 possibilities. Then for the person on the right of Alice, there are 4 possibilities. Now there are 7 seats left empty and 3 persons that can be somehow arranged on these 3 seats, which means 7 times 6 times 5 possibilities, which means 33,600 possibilities in total. Next, number D. We can look at Mia, Numa, and Otto as being only 1 person, and there would be only 8 seats. So we have to place now 5 friends on 8 seats, which means 8 times 7 times 6 times 5 times 4, or 8 factorial divided by 3 factorial. And then we sort of split Mia, Numa, and Otto again into 3 persons. At the same time, we split their 1 seat into 3 seats, and we can arrange them now in 3 factorial ways. So we have to multiply every combination before with 3 factorial, and we get the final result, just 8 factorial. Another way of looking at this problem is just to say, well, how many possibilities are there for the seats where Mia, Numa, and Otto can sit? So there's 1 possibility here, next one here, and so on until the last one here. And we see these are 8 possibilities. For each of these possibilities, we can arrange the 3 in 3 factorial ways. And once they are seated, there are 7 possible places for the next friend, then 6, then 5, then 4. This means for the remaining 4 friends. And we end up again with 8 factorial, which, by the way, is 40,320. Okay, let's get to example E. Taking Mia, Numa, and Otto as 1 person, and Rico and Sophie as another person on the other hand, we get now that we have 7 seats and only 5 persons, so we get the number of arrangement to be 7 factorial divided by 2 factorial, and again we split then Mia, Numa, and Otto, so there are 3 factorial arrangements for them, and Rico and Sophie, so for them there's 2 factorial arrangements, so we get the final result 7 factorials times 3 factorials. You can also in this case solve it using the other approach as we did it up here. However, you have to be careful here because it depends on where you place Mia, Numa, and Otto, how many possibilities there then are for Rico and Sophie. If they are placed here, Mia, Numa, and Otto, there are more possibilities from Rico and Sophie than if they are placed, for example, here, because then they can't sit here, Rico and Sophie. Let's get to the last example, number 5. Here comes the result. You can choose 2 out of 5 pasta types, 3 out of 9 types of gravy, and 1 salad out of 3. And here we go, we just multiply all the 3 of them, which means 1,890 different pasta plates.